So our last result is the sum of the geometric progression. As long as the ratio, absolute value of the ratio is less than 1, then it adds up, it converges, and then we even have a formula. It will be frequently the case that even though we know that the series converges, we might not be able to find what it is exactly equal to. But just saying that it converges is half the battle, just like with limits, because it is the difference between something that does or does not exist. So if we just say nothing but this, it converges. At least we're saying that that expression, that infinite expression over there, it is a number. We don't know what that is, but it is a number. Okay. So the illustration. So that's one illustration of how you have add numbers from 1. You divide by 2 every time, and you add up to 1. So either you do it. So that for more or less justifies the whole thing. So you exhaust square by cutting it every time in half, and that then you know that the end result will be 1, right? So this is the area is 1. You can also try the same with triangles. In addition to, we have an algebraic proof right there of the formula, but certainly having an illustration like this is just more sometimes more convincing. So you can have, for, let's see, if I divide a square, and that's supposed the area is x, and then I divide it into like this. Okay, then what's in the middle is x over 4. So I cut it into triangles, and what if I kept cutting it like this into smaller and smaller pieces every time in 4? So this one, the next one is, so this is x over 4, and this is x over 16. As x over 16. So and then x over 4, x over 16, and then I forgot what I'm trying to say here. Adds up to, so this ends up to, okay, so this is 1, I have 3 here, and here I have also 3. Okay, so then the series becomes 3 over 4 power of k, like this, k from 1 to infinity. Okay, so that is the series, and it gives me the whole triangle. So that is 1. Okay, so that's another explanation, another illustration rather than of the overall algebraic proof, that you can sometimes pick a geometric figure and you can exhaust it by cutting into smaller and smaller pieces and end up with the answer. Okay, which is kind of geometrically explainable. But this theorem is pretty much all we care about, and we use it when necessary. It is one of the most commonly used results in theory of infinite series. Well, there is one more example here of a geometric series. Let me try. Okay, so let's see. It's supposed to be a joke. Okay, so let's see, cartoon. So okay, so 1/2 of haircuts, but the joke is obviously that you only get half your hair cut. Okay, so and then you come, if you want a full cut, then you come back to cut what's left, and you cut half of that, and then and so you're left with 1/4, and then that 1/4 you bring back again, and you can cut in 1/2 again and again. And the conclusion is it lasts forever. I would question that. Is it really taking forever? Logically speaking. So it will take infinitely many steps, but is it infinite in time? The logic, my logic is that so once again, to get a full haircut, he would have to come back infinitely many times. So that's what he meant. But really, it would also logical would be to assume that every next haircut takes half the time than the previous one. So then we know from our formula that it will take how long? It will take, if the first haircut took 10 minutes, then the second time will take 5 minutes, then 2.5 minutes, and altogether it should take 20 minutes. Okay, so but otherwise it's a version of the Zeno Paradox. Remember, paradox of Achilles and the turtle running shorter and shorter distance to overtake the turtle, and it appears to be taking infinitely many steps. So did we talk about that when we talked about sequences? So it's the same logic pretty much, in just a more funny way expressed. But it does make sense then. It seems like there is a kind of paradox here, and it appears that he will never finish the job. But it does make sense if you sort of spend less and less time every time. Okay. So well, but then is it possible that under what circumstances this kind of process would be truly infinite? And the answer is yes, and that is the example of the what we call the harmonic series. One plus 1/2 starts the same way, but then we'll keep going with the reciprocals rather than with the powers of 2, for example. Okay, so once again, compared to the previous example, we have 1, 1/2, 1/4, 1/16, 1/16, 1/8, 1/16, and so on. This one grows slower, and you remember we had also some experimentation with the spreadsheet. Excel produced numbers that appear, like after 700 steps, we still had the sum was just above 7. Okay, so the conclusion is that's the theorem that's to be demonstrated. It diverges. Okay, and then once again, if you take this logic, then if the next haircut, actually the first haircut cut half, the second cut 1/3, then 1/4, 1/3. Well, that actually doesn't make any sense whatsoever. Okay, so never mind. But indeed, the sum is infinite. So diverges is a word that we use loosely, but sometimes loosely. But in reality, it not only diverges, it diverges to infinity. So you add only positive numbers, so there is growth, and that growth is unlimited. Okay, it is actually not very hard to explain why this is the case. Let me have this illustration again. That we saw yesterday. A comparison of integrals, comparing infinite series with improper integrals. So the first line, improper integrals from earlier this semester, and now what we're talking about is the second line, the series. Okay, so let's take this analogy a little bit further, and in fact you almost can see, well, the similarity is that in either case we are considering areas, and we're starting with the areas on intervals that are small, not infinite rather, and then we make them bigger and bigger and bigger, and that take the limit. Okay, but we can compare them now. Okay, we can compare them now, and so let's suppose that the blue one is in fact the harmonic series. So this is 1, 1, 1, 1/2, 1/3, 1/4. Okay, so that's my series right there. So the total sum, if I take all of these, let me try it. These, the whole area, the whole purple area will be, how do I show that it is infinite? I could try to show that it is larger than what? Than this. You can almost see that curve. Can you see the curve under those steps? This one. There is a curve there. Okay, so and then it continues on, and there is an area on the area under that curve. So step curve, a really simple curve, and together it gives me the purple one. The purple one gives me the sum of the harmonic series, 1 over n. Okay, is it infinite or not? I will show that a smaller area is infinite. Okay, the smaller area, which is this, this area, it is smaller, but still infinite. So it is smaller but infinite, which will prove that the bigger will also have to be infinite, right? So if I fit that yellow or yellow area underneath the graph of our series, fit it inside of the purple area, then that will prove what I want to prove, and which is if this area under the graph over the continuous function is infinite, then the bigger area will also be infinite. Okay, so the only thing that remains to be determined is what is that function. What is this function? The yellow function. So if this is 1 over n, then what's the function that goes underneath this? That step function. One over x. Okay, 1 over x, or technically it will be a 1 over x minus 1 plus 1. Oh, I want to shift it to the left, which means it's plus 1. Okay, 1 over x plus 1. So that curve that goes straight under my step function is, in fact, 1 over x. Well, 1 over x plus 1. So then the area is integral 1 over x plus 1 dx from 0 to infinity. Well, let's compute it. So sum 1 over n from 1 to infinity is, in fact, larger than or equal to integral from 1 to infinity 1 over x plus 1 dx. Okay, which we use what we know about improper integrals, so it will be limit with b going to infinity. Integral from 1 to b, 1 over x plus 1 dx. We integrate. What's the integral of 1 over x plus 1? 1 over x plus 1. What's 1 over x? Integral of 1 over x? Natural log. So, and this is just ln x plus 1. Okay, and it is between 1 and b, and it will be then limit b goes to infinity, ln b plus 1 minus ln 2, doesn't matter, and this is what we know by the logarithm. The logarithm goes to infinity. The logarithm, well, looks like this, y equal ln x goes to infinity. It does not have a horizontal asymptote or anything like that. It is increasing, and how do I know that it has no bound, the logarithm? So I need to know that it has no bound. To conclude that the limit is infinite, I need to know that this function is unbounded. So how do I know that it is unbounded?
You can take the limit of the natural log of x as x goes to
Yeah, but that is the question. So why is it going to be infinite? Well, ask yourself where your logarithm comes from. What's the meaning of the logarithm as a function? Where does the logarithm come from? What is logarithm anyway? Right, it is the inverse of exponential function. That pretty much does it, because remember how we do the inverses. This is the oops, maybe not like this, but this is the exponential function. So this is e to the x. Okay, so, and you remember we get the inverse function by flipping the original function about the diagonal like this, and what happens is the domain becomes the range and range becomes the domain. So then the domain of the exponential function becomes the range of the logarithm, and what is the domain of the exponential function is not if not everything. So there you go. So that's why it's unbounded. It is unbounded, and it is increasing. In other, we certainly can prove it by differentiation if necessary, but it is increasing, and then so which means that the limit will be infinite. The limit is infinite, so the area that we looked at was the area in yellow is infinite, so this is infinite, and then it is that area is smaller than the purple area because one contains the other. Okay, so and then if your area contains the area that is infinite, then your area is infinite. Okay, so that's why this is the sum of the harmonic series is right here, and we just demonstrated that it is infinite. Okay, so it takes some details to work this out, and there is a method to it. It's called the integral comparison test for series. So you compare, we will be comparing series to series, but also it's possible to compare series to integrals, to improper integrals specifically. So this analogy is certainly very productive. Not just analogy; it's a method pretty much. Okay, so let's not forget the meaning of this. Why we still I'll keep reminding you about that ultimately the series are meant to be applied to power series in approximations of functions. Okay, and so then there is one more. So one picture that we already saw previously is this. About those approximations, this one. Okay, so as you can see, the Taylor polynomials here in red, they increase in power, increase in degree, degree, and then they approximate that green function better and better. Okay, so that is one example, and so exponential function is approximated by these polynomials, and we already know what those polynomials are. We found their all coefficients, and we have not only these 8, we have all of them. Okay, because the exponential function is so easy to differentiate. But there is another one, and that is we could just take where's my geometric series. If we take geometric series, we can think of this as what if I replace r with x? Then I'm going to have on the left a power series. So geometric series. Geometric series. Sum a naught r n from 0 to infinity. Okay, so r is the ratio, and it converges. I'm just rewriting the theorem when the absolute value of r is less than 1. Okay. Now just rename things. I just rename r with x. Why? In order to emphasize the point that what we're getting is now a function a naught x. Well, let's drop a naught so it wouldn't be standing in the way. So it will be x n from 0 to infinity. It is in fact a power series. So E is a power series to begin with, and it converges once again when it is not applicable here, because we're not looking at a bunch of series as that the first line here is. We're looking at all the geometric series with various ratios, and then when the ratio, absolute value of ratio is less than 1, we have convergence. So that's why when is appropriate. Now, in the next line, we're not thinking about all of them one at a time, but rather looking at them all of them all together. Okay, all of them all together, meaning that x becomes a variable. X, that ratio becomes a variable, and that what we have over there is a power series which contains literally all possible geometric series in it. Okay, and then it is a function. Okay, and it converges on a certain interval. -1, 1. So for values of x between -1 and 1, the series will converge. Okay, and even though we know that we can verify it, I want you to see that this is a very different example from say this one. It does not converge everywhere. So this is fine. This one converges everywhere for whatever values of x you pick. The convergence will be there. However, this one it is quite clear that if I try to plug in x equal 1, we have divergence. Okay, so there you go. If I try -1, it also will have divergence, and on and on. Any large number of x chosen here will give me a divergence. So we can only speak of convergence on that interval. Okay, and then by the theorem now we know what the sum is. The sum of this series is in fact 1 minus x. Okay, so that is a nice example of, in addition to the example of the exponential function that we saw previously, of a representation, depending on how you read it, from right to left, from left to right. It is, in fact, if I read it from right to left, it is a power series representation of the function on the right. Okay, so that rational function this time, 1 minus x, is represented by a power series on the left. Okay, and as you can see, that function is actually 1 over x is defined everywhere except for one value. So this one, the difference between the left-hand side and the right-hand side is striking, because on the right, x is not equal to 1 is the only restriction. On the left, x has to lie between -1 and 1. So it's much more narrow than what we have on the right. In that sense, these are not the same function. They are only the same if we limit the domain to -1, 1 interval. To show that how this works out, there is another illustration here. Here it is. So the same idea as with the exponential function, but the difference is I hope quite visible. So once again, the second, third line are approximations by Taylor polynomials of different degrees: 0, 1, 1, 2, 3. So this is a constant function, linear function, quadratic function, cubic function, right? So that's the row in the middle. And then we keep going: 4, 5, 6, and 7. If we are looking at the behavior in the vicinity of 0, that is the point that we care about, this point over here, right here, then you can see how the approximation gets better and better, right? So it is, this one is a cut, very crude approximation. The tangent line in the next line over here is already better, but you can see the separation. The cubic is quadratic is better, cubic is even better, and so on. So they're getting better and better, but you can see that what is not going to happen is what is not going to be ever approximated at this part, right? So that branch of 1 over x beyond x equal 1 cannot possibly be approximated by a polynomial. And how could it? Because remember that this function has a vertical asymptote. There is a vertical asymptote in the for this function, and the polynomial can not only it has trouble approximating horizontal asymptotes. It will eventually go to infinity because these are polynomials, but also vertical asymptotes it is at least as bad because once again polynomials have no asymptotes. And even though over here they're getting steeper and steeper and steeper, like this, right? Getting steeper and steeper, they will never cross over to get this part. So this one will never be appropriately approximated, just as this never will. But if we limit ourselves to, as we plan to limit ourselves to the interval -1, 1, this one, okay, so without reaching 1, then these two functions will be, this function and its Taylor approximations will be very closely, will work well, except, well, you know, there will be always trouble at the endpoints over here on the right, because at 1, the function, the polynomial is growing faster and faster, but they will never be, will never have a vertical asymptote. Okay, so once again, that is the point of this, was to illustrate the difference between a function and its Taylor series representation. Okay. Okay, so we have right now two good examples of Taylor series representations. Taylor polynomials approximation, which is the same as Taylor series, and their exponential function. And remember, exponential function is e to the x represented by x to the n over n factorial, n from 0 to infinity. Okay, that's one representation. This is the other. There are no limitations on all x here. No limitations on the values of x. We'll have a convergence for every value of x that you can imagine. On the left, it's not the case. Okay, so next. So next we're looking at, well, we will just try to develop the theory of series so that we can have more and more representations of functions. And number one issue is how series behave relative to algebra. Just like with sequences, remember the limit of the limit of the sum is equal to the sum of the limits if you have two sequences. Similar properties we have for series. So that's what we're gonna get into. But first, let me elaborate a little bit on what on comparison. Comparison. So once again, this picture. The idea is the same. The idea is the same. Except I will be comparing not to an improper integral as I did, but I will be comparing two series to each other. Yeah. Okay. So comparison of series. So that is a familiar idea from sequences, and so what is it? What do we have? It is the idea comes from an inequality, from the idea of adding inequalities. That's pretty much it. What we're talking about. So if I have two pairs of numbers, sequences. So Sn larger than or equal to Tn for all n. Okay. So if I start adding them, so S1 larger than or equal to S2, T2, T1, S2 larger than or equal to T2. I add them together, I have S1 plus S2 larger than or equal to T1 plus T2. Okay, then if I also have S3 larger than or equal to T3, I could once again add them together, these inequalities. I have S1 plus S2 plus S3 larger than or equal to T1 plus T2 plus T3. And on, I will have S1 all the way through Sn larger than or equal to T1 plus Tn. Okay, so algebraic idea that also can be illustrated with this picture. Where's my picture? Where's my picture? Here it is. If you want to think in terms of areas, and we really do appreciate that, as you can see, you have a sequence of numbers. How many we don't know, and then one is higher than the other. then if we start piling them up together, the blue ones are higher than the orange ones. Okay, so if I pile up now the blue ones on top of each other, it's top, bottom right. Then the stack that I have built will certainly be bigger than the one made from the orange ones. Okay, so that's the whole geometric idea. And you know, so here you have four I don't know, little objects or some kind of building blocks put on top of each other, and the inequality is preserved. Then you can have 100, or you have 1,000, or have infinitely many, and they will still be can be stacked up in the inequality. So this is higher than the other is what we care about. Okay, that's what the inequality I'm trying to rely on. This last inequality. It follows from the inequality of the terms. Okay, so that is a very simple idea. So once again, if we have inequality of terms, then it produces the inequality of sums. Okay, the only difference is right now we are facing is what if we add infinitely many terms. So this is still finitely many terms. So we cannot really jump straight to series from this. We have to do it carefully with partial sums, and fortunately it's really not that hard if we are willing to assume the convergence. Okay, so suppose sum Sn, sum Tn. So the limits of the well, let's still write it n from 1 to infinity, n from 1 to infinity. Suppose both of them converge to begin with, and secondly, Sn less than or equal to Tn for all n. Then the sums have the same inequality. Okay, but the assumption is to begin with that they converge. So convergence of the one does not necessarily imply convergence of the other. And in contrast from that example that we just had when we demonstrated that the harmonic series diverges, we demonstrated that one was divergent that the other one did too. Now this one is assume that both of them kind of convergent, then you can compare. Where does the difference come from? And it comes from the fact that the terms were all positive. Both the function is positive, and the terms of the series, the bottom row, are also positive, which means that there are only two outcomes, and those are either it goes to infinity or it does not go to infinity and then it converges. So there are only two possibilities. When there is no such restriction, which is where we are right now, it is possible that these two could be positive and negative. Positive or negative, then it is possible that our summation will produce partial sums that go up and down, up and down, up and down. So whether even if it is bounded, it might still diverge. So sum of partial sums, the limits of partial sums, such as this one, might still be divergent, even though it is bounded. So this theorem only works when both of the series are to assume to begin with to be convergent. Okay, then for example, let's use that fact. So let's assume, as an example, and you have to assume that the sum 1 over 2n plus 1 converges. Okay, then I could compare this series to the series that is familiar, and then I compare 1 over 2n plus 1 plus 1. It is less than or equal to 1 over 2n. So we assume that this series converges, and then I compare this series to an old familiar one. Old familiar, meaning it is in fact the geometric series with ratio equal to 1/2, which means that when I do summation, so by theorem, there will be still inequality between these two series. 1 over 2n plus 1 less than or equal to sum 1 over 2n, n from 1 to infinity. And since it's old and familiar, we know what the answer is. The sum of these numbers, starting with 1/2, 1/4, 1/8, will be equal to 1. So we discovered that not the sum is, but at least it is an estimate about it. So conclusion is that the sum of 1 over 2n plus 1 is less than or equal to 1. It is under the assumption of convergence once again. You can imagine there when that fails if the series that we start with actually alternate signs, for example, then we don't know. Okay. Okay, now algebraic properties. So the comparison is, there will be more comparison tests. The tests, this is not technically a test, it's just a comparison. You just, because you assume convergence and then you have the number. Comparison test, similar to this analysis, will be telling if this one converges, then so does the other one. Or if this one diverges, so does the other one. So that would be the test for us to, very useful test, but a little bit later. Right now, algebraic properties, or algebra with series. So for example, if I have this series 3 divided by 2 to the n from 1 to infinity. Okay, so as you can see, it is almost a familiar series because we divide by the powers of 2, but that 3 stands in the way. Well, yeah. Well, technically, this is a geometric series already. Let me take a different one. How about well, let's ignore the fact that it is a geometric series. But the question is this equal to 3? Can I factor 3 out? And that is not an obvious answer that we can. Okay, so does it make sense? So it certainly makes sense, but it does require some thinking to confirm that it makes sense, because if the notation that we use does suggest that we can factor 3 out, just like we factor 3 out from differentiation, from integration. It is literally factoring, and there is some symbol that stands for differentiation or integration, and then you can pull it out. Let's say 3, 1 over x dx, whatever, and it is equal to 3 integral 1 over x dx. So something like that. The logic is the same, and it is also whenever it is just as challenging, because every time we have something that involves limits, then we have to be careful, and it might not be as easy as it seems, because after all, in this expression that we have infinitely many terms. So you have 3 divided by 2 plus 3 divided by 2 squared plus 3 divided by 2 cubed, infinitely many terms. And can I factor 3 out? 1 over 2 plus 1 over 2 squared plus 1 over 2 cubed. And there is no such thing, so careful about doing any algebra with wherever there is dot involved, because it means that there are infinitely many terms, and it means that there are no rules of algebra like this. So it looks like simply factoring. You can say it is, or what is it? A distribution property of addition and multiplication. But those rules apply only to when you use 2 terms. So you can then do 3, 4, 5 terms. Doesn't matter how many terms you use. It's okay to do something like that, but only when that process ends. So you can have 1,000 terms together, and you can factor 3 out. That's all fine. When you have infinitely many terms, you cannot just do it in such a cavalier way, And let me give you an example. So even though this is true, suppose we try to apply factoring or distributive property with something else. How about, what if it's not, how about it is 0? So say, what is it? Hold on, what is the example that I have in mind? Factoring. So under what circumstances the factoring would not work? So if we have harmonic series, say 3 over n, and is it equal to 3 1 over n? So that is the question. Is it legitimate to factor 3 in this example rather than the original example? And the answer is no. And the answer is no, because once again, you're not allowed to do algebra with, well, you're only allowed to do algebra with numbers. Yeah. So no. And why? These are not numbers. And it's not that they're series. They are, but the problem is that these are also series. The first example, we have series, and we are justified. We will justify. So the answer is yes. We are justified. We will justify that it is indeed possible to factor 3 out in the first example, but not in the second example. Why? Because the first example is the series is convergent. The series is convergent. Both of the series are convergent, and that is why we are talking about numbers. A convergent series gives us at the end of the limit a number. So these are 2 numbers. So these are 2 numbers, and that is why it is okay to do algebra with them. These are not numbers. So these are in the second example. Since the series diverges, then we cannot do algebra with anything but numbers. Okay. So anyway, the way where is it? Here it is. The way we state it, we put it in the form of a theorem. It is called naturally the constant multiple rule. Is so suppose we have a sequence. As a sequence. From a sequence, as always, we will form a series. C is a real number. That is the multiple, and then we have two series to worry about. The original series. So suppose. And the one that is multiplied by C. So suppose an from 1 to infinity converges. Okay. Then so does this other one. Term by term multiplied series. Every term in this series is multiplied by that number. Okay. It is a totally new series, and then we say, it is pretty much the same as far as the outcome is concerned. Both of them converge, and then there's a formula between them naturally. So CAN, n from 1 to infinity, is equal to C, as if we can factor C out, AN. Okay, so the proof follows from from the constant multiple rule for sequences. So if a sequence converges, then its multiple also are convergent. And then in terms of the partial sums, that's what we discovered. So I guess let me write it out just for once how that works out. So that's the idea. That's the idea. If you want to be specific, this is what you do. You always proceed the same way. You do the partial sums. So you take you go this way. AN converges. Converges means what? That the sequence of partial sums, so this would say PM is equal to the sum n from 1 to m, AN converges. Okay, so PM converges. So only not the infinite summation, but finite summation, which means that it is nothing but a sequence of numbers. So then, as m goes to infinity. Okay, and now consider its multiple. So if I'm talking about, say, QM is equal to the sequence of partial sums of the second series, it is sum n from 1 to m, CAN, okay? And then once again, at this point, we use the fact that there are only finitely many terms in this sum, which means that I'm totally justified factoring C out like this. Okay? And I have AN. So then what? It converges too. By the constant multiple rule for sequences. This is what I'm talking about. I guess this is what I should have written here. It is equal to QM is equal to CPM. Okay, so then what we have here is PM converges. That's what the constant multiple rule for sequences says. PM converges, then so does CPM. That's what that rule says. And we apply to the sequence of partial sums. Okay, so if one converges, then the other. Okay, and so then the sequence of partial sums converges, which means that by definition the series converges. This means by definition that the series CAN converges to. Okay, the end of proof. Okay, all right, so see you tomorrow.